Welcome back to the deep dive. Today we're going to tackle something huge. We're
Yeah.
going on a journey from like ancient clay marks all the way to the microchips that are probably in your pocket right now.
That's right. It's the history of computing. But not just a list of dates. We want to see the big pivots, the inventions that really changed things.
Exactly. More like the why behind it all.
Precisely. And our mission today is to really dig into the basic computing periods and then the electronic generations. We need to see how these ICT inventions shaped, well, everything, civilization itself.
And crucially, how that history connects to you, especially if you're heading into tourism or hospitality.
Absolutely.
Hmm,
Because understanding the why behind the systems you use every day, that's just as important as knowing how to click the buttons.
Good point. Okay, so before we dive in, let's quickly set the stage. What actually is a computer, fundamentally? Our sources mention three key things.
Yeah, basically, think of it as a programmable machine. It's designed to work with information. And its three main characteristics are, one, it responds to specific instructions you give it.
Right.
Two, it can run through a whole list of those instructions that you've stored beforehand. That's, a program.
Right.
And three, it's really good at storing and then quickly finding huge amounts of data, which, interestingly, means the very first computer wasn't a machine at all.
It was a person. I find that fascinating.
It really is. The word computer, it first popped up in 1613, and it meant a person, usually highly paid, whose job was just calculating, doing sums all day.
Wow. So that kind of sets us up for that earliest period, the pre-mechanical age,
Mm.
when these human computers needed, well, help.
Exactly. This age runs roughly from 3000 BC up to about 1450 AD. And the technology here is all about helping human memory and calculation.
Like simple tools.
Very simple. Think of tally sticks. Just, notches on wood or bone to keep track of numbers or quantities. It's like the world's oldest spreadsheet, basically.
Like that.
And then, of course, the big one, the abacus. Invented way back in Babylonia, maybe 2400 BC. Still used today in some places. It made basic arithmetic faster, more reliable.
But still, the person had to do all the work, all the thinking.
You're right.
The abacus didn't think for itself.
Not at all. It's an aid. Moving towards actual automation, that took a really long time. Which brings us to the mechanical age, say 1450 to 1840.
Okay, so now we're trying to build machines that do the calculating for us.
That's the leap, yeah. You get these really interesting, sometimes kind of eccentric inventions, like Napier's bones in 1614.
Napier's bones.
Yeah, clever tool for multiplication, division, square roots. And then the slide rule, 1622, based on logarithms, brilliant for complex math. Engineers used them for centuries, but funnily enough, couldn't do simple addition or subtraction.
Huh. Weird limitations. And then we get the more famous attempts, right? Like Pascal.
Blaise Pascal, yes, his
Yeah.
Pascaline, 1642, a beautiful mechanical calculator. But it had problems. It could only add and subtract, and it was incredibly expensive, just not practical. Then Gottfried Wilhelm Leibniz came along with his stepped reckoner in 1672. Now, that was a step up. It could actually do all four basic functions: add, subtract, multiply, divide, automatically.
That sounds much more like a calculator. But the real visionary, the one everyone points to, is Babbage, isn't it?
Charles Babbage, absolutely. He's kind of the conceptual grandfather of the modern computer. First, he designed the difference engine around 1822, specifically for calculating polynomial functions like mathematical tables.
Okay.
But his next idea, the analytical engine, designed around 1834. That was the true breakthrough. It was designed to be a general-purpose mechanical computer. It had a mill, like a CPU.
A processor.
Exactly, and a store memory. And it could take instructions from punched cards. It was, revolutionary for its time.
And it wasn't just Babbage. There was Ada Byron, right? Augusta Ada Byron, later Countess of Lovelace.
Yes. Working with Babbage around 1840, her contribution was immense. She realized his machine wasn't just about numbers. It could manipulate symbols according to rules.
So like algebra, not just arithmetic?
Even beyond that, she saw it could follow algorithms. She wrote what many consider the first computer programs for the analytical engine, even suggesting using the binary system. She saw the potential for computation beyond just crunching numbers. She's rightly called the first programmer.
That's incredible. So that idea, programmable symbols, is key. Where do we go from Babbage?
Well, that symbolic idea takes us towards the electromechanical age, roughly 1840 to 1940. Now we start seeing electricity enter the picture, mainly through communications.
Oh, okay. Like the telegraph.
Exactly. The telegraph, Morse code around 1835, then the telephone in 1876, radio in 1894. These technologies taught us how to harness electrical signals for, sending information quickly over long distances.
So people are getting used to electricity doing things. Does that lead to electric computers?
Eventually, yes, but first through these massive electromechanical machines. They used electrical switches and relays, not purely electronic components yet. The Harvard Mark I from 1943 is a famous example.
The beast you mentioned.
Yeah. Yeah, it was enormous. 50 feet long, 8 feet high, weighed 5 tons. Slow, clunky, programmed with paper punch cards fed into it. Painstaking work.
Wow.
Around the same time, actually a bit earlier, in Germany, Konrad Zuse built the Z1 between 1936 and 38, often considered the first freely programmable computer, also using punch tape, but still electromechanical.
So these showed it could be done, but they weren't quite the electronic revolution yet. When did that happen?
That kicks off with the first electronic generation, roughly 1946 to 1958, and the defining technology here, the vacuum tube.
Ah, the iconic glass bulbs. That's the image everyone has of old computers, right? Filling up rooms.
Exactly. Think big, hot, and expensive. The ENIS is the classic example, built for the U.S. Army to calculate artillery tables. We're talking 30 tons, 680 square feet of space.
Just massive and hard to use, I imagine.
Extremely. It relied on machine language, which meant literally programmers had to flip switches or plug wires to represent ones and zeros for every single instruction. Very rigid, very error-prone.
So computers existed, but they were basically only for huge government or military projects. They weren't practical for much else.
Not really, but they proved large-scale electronic computation was possible. The big conceptual leap came a bit later, with the EDVRE, around 1952.
What was different about EDBE?
It introduced the idea of the stored program computer, largely thanks to thinkers like John von Neumann. This meant the computer's internal memory could hold both the data and the program instructions.
Ah, so it didn't need constant rewiring for different tasks.
Precisely. That's the architecture basically every device uses today. Your phone, your laptop, they all store programs in memory. This led directly to the UNIVAC I, the first computer actually sold commercially. Still huge, still expensive, but a step towards business use.
Okay, so vacuum tubes got us started, but they were clearly limited. This feels like the moment where things had to change, right? Where the real acceleration begins.
You got it. Now we hit the revolution in scale. We move from these room-sized behemoths towards something, well, smaller and faster. How do we get past the size and the heat of vacuum tubes?
Transistors.
The transistor. That's the heart of the second generation, roughly 1959 to 1964. This tiny little semiconductor device was a complete game changer.
How much of a difference did it make?
Huge. One transistor could do the job of maybe 40 vacuum tubes. Suddenly, computers became dramatically smaller, faster, much cheaper to build, and way more energy efficient. They didn't generate nearly as much heat.
Okay, that's the moment the computer starts moving out of the military basement and maybe into, like, big companies or research labs.
Exactly. And programming got easier too. We moved away from raw binary, those ones and zeros, towards symbolic or assembly languages. Programmers could use short words or mnemonics for instructions, which was a massive improvement. They also started using magnetic core for memory.
So smaller, faster, easier to program. What's next? How do we get even more power?
The third generation, 1965 to 1970. The key invention here is the integrated circuit, the IC, or as most people call it, the silicon chip.
Putting multiple transistors onto one chip.
Not just multiple hundreds, then thousands. Miniaturizing transistors and etching them onto a tiny piece of silicon. This just turbocharged everything. Speed and efficiency went through the roof.
How fast are we talking?
Calculations in billionths of a second, nanoseconds. This power increase allowed for the development of actual operating system software that managed the computer's resources.
So the computer could sort of run itself more.
In a way, yes, and it made developing software easier. We also saw the rise of high-level programming languages like BASIC. Suddenly, programming became accessible to a much wider group of people, not just hardcore engineers.
Okay, transistors made them smaller, ICs made them faster and smarter. This feels like we're really getting close to the computers we know now.
We are, because the fourth generation, starting around 1971 and arguably continuing today, is defined by the microprocessor.
The CPU.
The CPU, exactly, the central processing unit. This was the ultimate step in miniaturization up to that point, putting thousands of integrated circuits, essentially the entire brain of the computer, onto a single tiny silicon chip.
And that That changes everything, doesn't it?
Completely. The microprocessor is what led directly to the personal computer. Things like the Apple II. Suddenly, a computer wasn't something that filled a room, it could sit on your desk.
And that's when we get things like mice and clicking on icons.
Yes. The development of graphical user interfaces, or GUIs, happened in this era, made computers visual, intuitive, instead of just typing commands. And crucially, the networking infrastructure started being built, laying the foundation for what would become the internet. Handheld devices also started appearing.
It's just mind-blowing. From ENIAC weighing 30 tons to all that power on one tiny chip.
It's a direct line, though. Vacuum tube to transistor to IC to microprocessor, each step building on the last, driving that incredible miniaturization and increase in power. That speed and connectivity underpins, well, almost everything in modern life.
So if the microprocessor defines our current era, where are we headed? What's the fifth generation?
We're actually living in it right now. The fifth generation is all about artificial intelligence, AI. It's also about parallel processing computers, doing many things at once and exploring things like superconductors.
So computers that can think or learn.
No, that's the goal, yeah. Devices that can respond to natural human language, learn from experience, and organize themselves. We're already seeing it everywhere, aren't we?
Okay.
Voice recognition on your phone, that's fifth-gen tech.
Recommendation engines on websites.
Definitely. Dynamic pricing in travel, sophisticated data analysis. AI is already deeply embedded, especially in service industries.
Which brings us perfectly to our final section. We've traced this amazing history from tally sticks to AI. Why does this journey, this evolution, specifically matter to someone listening who's maybe studying or planning a career in tourism and hospitality?
Oh, it matters profoundly because the entire modern tourism and hospitality industry is built on the foundations laid down in those generations, especially the third and fourth.
How so?
Remember when we talked about the IC allowing calculations in billionths of a second? That speed, that processing power, is why a hotel's property management system, the PMS, can do so much so quickly.
Like checking someone in, taking payment, updating housekeeping.
All at the same time, exactly, across potentially hundreds of properties in a global chain. That seamlessness relies entirely on that speed and the networking developed in the fourth generation.
It enables the convenience that customers just expect now, doesn't it?
Absolutely. Think about booking a vacation. You, as a traveler, go online, you check flight times, compare routes, buy tickets. You browse hotels, maybe look at Airbnb, check reviews, book your room. You might even book a guided tour for Tuesday afternoon.
All online, probably on your phone.
Right. And you expect to do that instantly, 247, from anywhere. That entire ecosystem only functions because of the speed, the databases, the networking that evolved from ICs and microprocessors.
And it's not just the customer side. Businesses rely on it too. Retail, trade. Selling tours or hotel rooms online lets businesses reach a global market with relatively low overheads.
And buyers can compare prices instantly, choose delivery or check-in options. It's all powered by that computing history. Even government plays a role, you know. Tourism boards use sophisticated systems to track visitor data, market destinations effectively, manage attractions.
Right, data analysis is huge there.
Huge. And think about money. Online banking, mobile payments, instant transfers. They make transactions incredibly smooth for both travelers and businesses. You don't need to carry huge amounts of cash.
And customer service too. Real-time chat support, chatbots answering basic questions, video calls.
All dependent on reliable, fast communication networks and powerful processing, which again traces back to those key generations. And looking forward, the fifth generation, AI is already changing things.
Wow.
Dynamic pricing is a big one. Hotels and airlines adjusting prices minute by minute based on predicted demand. Hyper-personalized marketing showing you ads for destinations you might like based on your search history. AI is optimizing operations and tailoring experiences. This history isn't just history, it's the bedrock of the industry's present and future.
What an incredible journey. It really is staggering to think we went from someone scratching numbers onto clay, or a person being the computer in 1613, to this global web of AI-powered systems in, well, mostly just the last 80 years or so since vacuum tubes.
The pace of change is just phenomenal. So to help kind of solidify all of that, here are a few key terms from our discussion that really mark those big leaps.
Okay, good idea.
We've got vacuum tube, transistor, integrated circuit or IC, microprocessor, going back, the analytical engine, ENIS, GUI, the graphical user interface, and of course, artificial intelligence or AI. Maybe even tally stick right at the beginning.
Good list. And finally, as you think about how all this applies to your future, maybe in tourism or hospitality, here are a couple of questions to ponder, just to get you thinking.
Right. First one, thinking about that rapid change from vacuum tubes to microprocessors and now AI. What specific tools or systems used today in tourism and hospitality? Maybe something you use regularly, do you think might become completely obsolete or totally automated by fifth generation AI within, say, the next 10 years? And try to think beyond just basic chatbots.
Ooh, that's a tough one. Okay, and the second question.
Second, we saw how computing went from these super expensive, exclusive mechanical devices like the Pascaline to much cheaper, mass-produced electronic computers. That shift really changed who could access information and calculation power. How does that history mirror the digital divides we see today in the global travel industry? Think about access to booking platforms, data, or marketing tools maybe in developing countries versus developed ones.
Two really great questions to chew on. That brings us to the end of this deep dive into the ancestors of modern computing. Thanks for joining us.